Hello and welcome everyone. Today we're going to be learning about audio equalization using fast Fourier transforms. We'll explore the core concepts behind how fast Fourier transforms work and how we can utilize this algorithm to allow us to equalize audio. So what is audio equalization? Audio equalization is a process of adjusting the balance between different frequency components in an audio signal. Think of it as a fine-tuning tool that allows you to control the volume of different frequencies in your audio. For example, you can boost or lower the bass volume, or the same with the mid-range or treble frequencies. Audio equalization is essential to and can be applied in many different contexts. Differently configured hardware can sound vastly different, so it's essential to equalize or edit our audio to make the same signal sound the same way on different speakers or hardware. Audio equalization features are available on almost every application or system that deals with outputting sound, and real-time audio equalization is essential for live music and streaming or broadcasting scenarios. We've all most likely seen or used an audio equalizer at some point, even if it's something as simple as adjusting the EQ in Spotify. However, let's consider how an application like Spotify even achieves this. Sound is a form of mechanical wave that travels through a medium such as air or water. When an object like a musical instrument or our vocal cords vibrate, it creates pressure waves in the surrounding air. We record these continuous sound waves using discrete samples at a particular frequency and store the information as an array of numbers that corresponds to a pressure over time graph. So when Spotify plays a song back to us, it's essentially playing us back a one-dimensional pressure over time signal that's been converted back to sound. So how can Spotify discern the individual frequencies in this complicated signal and filter and boost the required ones? Intuitively, we can tell from this that there must be some way to separate a one-dimensional signal composed of many individual frequencies into its component frequencies and discern them. This is where the Fourier transform comes in. The Fourier transform is a mathematical operation that transforms a signal sampled in time or space to the same signal sampled in temporal or spatial frequency. If we have a one-dimensional signal of pressure or amplitude over time, we can use a Fourier transform to convert this into a frequency over amplitude graph. Essentially, the Fourier transform allows us to see what the separate frequencies in a signal are and how prominent or loud they are as well. A Fourier transform is typically used to refer to when this operation is done on some continuous signal with an infinite number of samples. However, this is a platonic ideal, and computers use discretely sample sound at a given rate. So a variation of this operation, quite reasonably called a discrete Fourier transform, is used. A fast Fourier transform is an algorithm that efficiently computes the discrete Fourier transform or the inverse discrete Fourier transform of a sequence. So, if a fast Fourier transform is a specific efficient algorithm for computing the discrete Fourier transform of a signal, how do we compute the discrete Fourier transform? Imagine you have a sequence of n data points that represent an audio waveform sampled at discrete time intervals, and our goal is to determine what frequencies are present in the signal. The discrete Fourier transform as an operation can be written in this form, where big N is the number of samples, little n is the current sample, k is the current frequency belonging to between 0 and n minus 1, xn is the sign value at sample n, and xk is the ultimate DFT, which includes information on both the amplitude and phase. This measures how much the input sequence resembles a sinusoidal wave of frequency k over big N at each step, and the result is a complex number for each frequency component, where the real part represents the amplitude and the imaginary part represents the phase. Now that we have a high-level overview of what a fast Fourier transform is and what it can be used for, let's try and utilize this algorithm ourselves in code. For our first example, we're just going to be working with some basic sine waves. As you can see, I've written 3 sound files that each contain a pure sine wave of a different frequency. I also have another sound file that contains all 3 sine waves played together simultaneously. I can use Julia's built-in plot function to plot how this wave looks, and we can see that the first wave has a lower frequency than the second, which has a lower frequency than the third. We can also see that if we plot the fourth wave with the combined frequencies, we get a much more complicated looking signal. We can use Julia's built-in FFT function to take the fast Fourier transform of any of these waves. You can see if we take the first wave, it discerns only one frequency because it's a pure sine wave. Same for the second and the third. If we plot all these three in the same graph and simultaneously take the fast Fourier transform of the fourth combined wave, we can see that the same frequencies are being discerned. However, in the FFT of the combined wave, they're all at the same amplitude because all of the notes are played at the same volume. Now that we can discern the separate frequencies, we can filter them. We can boost the volume of some parts and reduce the volume of others and apply equalization as we feel. For the following equalization example, I'm going to be using the song Stand By Me. We can first read in the sound file, and if we take the FFT of it using Julia's built-in FFT function and plot that, we can see all the different frequencies available in the sound file. We essentially want to remove or boost some of them and then take the inverse FFT to convert it back into sound. That's how we'll apply our equalization. We want to apply high and low pass filters to our audio. Essentially a threshold under which no frequencies will be retained and another threshold above which no frequencies will be retained, only keeping the frequencies between those two bands. We can define two variables for this in Julia, and for the sake of the interactivity, they're going to be sliders, but you can think of them as just normal variables. After we extract the sampling rate of our sound and the number of samples in the FFT, we can feed these into Julia's FFT frequency function to get an array of all the frequencies that were in our FFT. We can now see how we're applying our equalization. The first two lines simply create the low pass and high pass filter masks. These are Boolean masks for frequencies in the Fourier transform. Low pass filter mask is true for all frequencies less than or equal to our low pass cutoff, and the high pass filter mask is true for frequencies greater or equal to the high pass cutoff. We then reshape these 1D Boolean masks into the same shape as the original Fourier transform signal, and we invert the masks. We then multiply the original Fourier transform signal by the combination of the low pass and high pass filters. This combination is performed using element-wise multiplication within the inverted masks. This operation effectively keeps only the frequency components within the specified range. We then calculate the inverse Fourier transform of our filtered FFT, resulting in a time domain audio signal that represents the filtered version of the original audio. And finally, we play back our filtered audio. Thank you very much for watching this video, and I hope this provided some insight on how we can use fast Fourier transforms to equalize and filter audio.